Today I'm going to talk to you about shot noise in forward biased diodes. The outline will be, I'll first introduce you to the mechanism of shot noise generation in forward biased PN junction diodes. Then I'll show you a diode circuit that can be used for measuring shot noise with the help of the SSA-X source signal analyzer baseband input, and then I'm going to show you results of that input into the very sensitive receiver of the SSA-X, and then I'll summarize what we learned today about shot noise. Okay, so let's talk about the source of noise, in this case, shot noise in diodes. We'll start in the top left right here. We have a PN junction diode right here. There's the diode symbol. We have the anode, the positive terminal, cathode, the negative terminal. We're putting current through with a current source in the direction of the arrow, meaning that this is a forward biased diode. Now, if we looked at this diode from a semiconductor point of view, looking at the band diagram, I think we can learn a lot about how current conducts in a diode and also what is the source of this noise called shot noise. So let's kind of get oriented right here. So on this side right here, we have P-type material, and this lower level right here is called the valence band, and the upper level is called the conduction band. And it's a P material, meaning that there's many holes. So all these little circles right here represents a high density of holes, which is a lack of an electron in this P material right here. So the holes are the majority carriers right here. But there are a few electrons in the P material right here, and they're called minority carriers. On the opposite side right here, we have N-type material. An N-type material, the charge carrier are electrons, and so we have electrons right here in the conduction band that are free to roam right here, and we have a high density of them since it's an N-type semiconductor. Since there's so many electrons, that suppresses the number of holes right here. And so this is minority carrier holes in the N semiconductor material. Now, this is a forward bias diode, and we can see that by these lines are called the Fermi levels right here. There's a Fermi level in the P material, and a Fermi level in the N material. And the difference in heights between these two right here represents the forward biased potential in this diode. And typically the difference between those two levels would be on the order of 0.6 or 0.7 volts between the two Fermi levels right here. Now, there's different current mechanisms in a diode, but in a forward bias diode, the primary mechanism for current flow is called diffusion. So on the N-type material side right here, we have lots of electrons right here, high density of electrons right here. In the P-type material, we have very few electrons. Now, they're minority carriers. So in diffusion, the carrier motion is always from the high carrier density area to the low carrier density area. So these electrons will start diffusing across this junction as long as this potential barrier right here is not too large. And when we're forward biased, this potential barrier here is quite small. So this is on this axis right here, we have electron energy, in this axis we have position. And the potential is slightly increased, but many of these electrons have enough energy to surmount that barrier and be diffused and emitted across this barrier. Now, it's interesting, an electron right here on the right-hand side is majority carrier, and they live a happy life. There's so many electrons, nobody's interfering with them. But when they start diffusing to the left-hand side in the P materials, these electrons encounter a region that is hole-rich, many holes. And so when these electrons encounter the many holes, they're going to recombine. So that electron and that hole there will combine and annihilate each other. And so quickly, as the electrons diffuse across the other side, they are essentially eaten up by these holes right here. And that eating up process is very fast. And over a small distance, all the electrons are eaten up. So that eating up of holes in electron means that there'd be a deficit of holes here. But the external circuit will take away electrons right here, creating more holes to keep this population of holes replenished in a steady state manner. So I first talked about electrons diffusing from the N-type material to the P-type material, then get eaten up by the holes, and that causes a diffusion current. Similarly, in the P-type material, we have many holes. They're the majority carriers. And on the right-hand side in the N material, we have very few holes. So there's a concentration gradient. And so these holes will want to diffuse over to the N-type material. When they get to the N-type material, though, they're going to encounter many, many electrons that are very hungry, and they'll want to recombine. And so these electrons will then recombine with the holes, and they'll annihilate each other. But if that kept on forever, then we run out of electrons. So then what we have is we have the external circuit supplying electrons right here to the diode to keep this population of electrons at a steady state value. So that's just telling us what is the nature of current in a forward bias diode. And it is diffusion current of both holes and diffusion current of electrons. But we're talking about noise here. What is shot noise? Well, shot noise is all about the fact that these electrons right here, when they diffuse across the junction, are not doing that on a regular rhythm. It's not like diffuse, 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 diffuse at a regular interval. It can be diffuse, 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 diffuse. So I illustrate that right here by saying that the regularity of diffusion and recombine is not perfect. And so we get a noise mechanism right here where a little current spikes right here are not uniform in time. And that's the nature of shot noise, both in the electron diffusion shot noise and the hole diffusion shot noise. And so that's the fundamental origin of shot noise. It's always associated with electrons or holes going over a potential barrier. And right here, this is a potential barrier right here, the small little rise in level. So if we're describing a noise mechanism, a shot noise mechanisms, we use this formula to describe the magnitude of the shot noise. So the RMS value of the shot noise right here, not the DC current, but the value of the noise. The RMS value is the square root of 2 times the charge on an electron, which is 1.6 times 10 to the minus 19 coulombs, times the DC current, this one right here, the DC current that's flowing through the diode. So the more DC current we have flowing, the more shot noise we have. And also we have to take into account the measurement bandwidth. The larger the bandwidth, the more noise that will be allowed, and the more lumpy the noise will be. So I'll call this lumpy noise right here. So I say, notice the lumpy nature of current flow due to random diffusion and recombination times across this potential barrier. And we just got done with a thermal noise talk like this, and I note here that there is no thermal noise in this situation. It's just shot noise in a diode that's forward biased. Let's look at this a little bit more and dive into that a little bit more right here. So this is a kind of a more detailed look at the shot noise in a forward biased diode. So let's first start talking about the electrons right here in the N-type material. They're diffusing across over to the P-type material. And notice this cartoon, it says the hole right here is welcoming the electron and saying, welcome to hole land. You only have 10 nanoseconds to live. So when these electrons diffuse over there and see this sea of holes, they quickly die. They recombine and annihilate each other. And so that population of electrons that diffuse across right here will quickly decrease. And the slope of that line is going to be very important, because the slope of that line is going to determine how much current is flowing in that diode. And that comes from this diffusion equation on the left-hand side. Here it says that the diffusion current of electrons from the N side to the P side in units of amps per centimeter squared is the electron charge times something called the diffusion coefficient, which has units of centimeter squared per second. A typical value would be 35 for silicon. And then this right here is the slope. How fast does the number of electrons in the P material right here. This is the number of electrons in the P material. How fast does that die off as a function of distance right here? And that slope right there is really important because that determines how much current is flowing in the diode. So the slope of that line gives you how much current for electrons are flowing in the diode. Similarly, we have holes right here that are majority carriers, and we have no holes hardly at all in the N-type material. They will start diffusing across the barrier. And here's a sign that says, "Welcome to electron land. You have 10 nanoseconds to live." So as those holes diffuse to the N-type material, they're quickly eaten up by the large population of electrons. And again, the slope of that line right here, the diffusion current for holes is going to be the charge on a hole times the diffusion coefficient for holes times the slope of that line. How fast does the P carrier in the N material change with distance? So the slope of that line gives you how much hole current is flowing. So there's both electron current flowing in a p-n junction forward bias diode, and there's also hole current in a p-n junction forward bias diode. The external power supply right here on the N side supplies electrons to make sure that we don't get a depletion of the number of electrons in this valence band region right here. So we can have steady state electron populations. And the same thing right here, as holes diffuse to the other side and recombine, we need to remove electrons from that side to keep the whole population at its steady state value. And the lumpy nature of this diffusion process and recombination right here, it's not rhythmic, it's very non-rhythmic. That is the nature of shot noise in a semiconductor forward biased diode. Well, I'm going to do a little bit of support here. So let's look at this equation right here for shot noise right here and see, let's quantify that. How big is shot noise? Okay, so on this column, I have the DC current that's flowing through the diode. And on these other columns, I have how much bandwidth we're making the observation in, from 1 hertz to a kilohertz to a megahertz to a gigahertz. And so if we had 1 megahertz of bandwidth on the receiver and we had a microamp of current, we'd have 5.7 times 10 to the minus 10th amps of shot noise. Let's look at a kind of a moderate level here. Let's go to 10 milliamps of current here. 10 milliamps of current with 1 megahertz of bandwidth, we would have 57 nanovolts of nanoamps of current right here. So you get into big currents like 100 amps right here, then you're kind of getting in almost into millivolt range right here for shot noise. So a wide range of shot noise values depending on the current that you have in the diode and the bandwidth of observation. Let's look at some other viewpoints on shot noise. So here we're looking at the spectral domain view of shot noise. So in this circuit right here, I have a diode, and I'm putting a current source with 10 milliamps of current into that diode right there. So it's forward bias with 10 milliamps of DC current. The DC current produces shot noise, and this current, right, this source right here represents the shot noise of that diode, not the DC noise, but the shot noise. And I'm going to AC couple it right here so that the shot noise can AC couple to an output 50 ohm resistor load right here. And we'll be doing a measurement shortly with a 50 ohm load on this SSA-X instrument right here. Now I'm going to assume, which is probably a wrong assumption, that this current and the shot noise right here will all flow through the capacitor to the output. If that's true, then I can do a calculation saying that the voltage across this 50 ohm resistor right here is going to be 50 volts times the current of this shot noise right here. And the current's going to be 2 times Q times IDC, which in this case is 10 milliamps times the bandwidth. And we'll let the bandwidth be a variable. We'll make it a 1 megahertz variable. So if we put 1 megahertz into the shot noise equation, and multiply by 50, we're going to get 2.8 microvolts of voltage across this 50 ohm resistor from shot noise of this diode right here. Now I can convert that to other units. If I want to convert it to watts, I'd go 10 log of V squared divided by 50, and I'll get minus 128 dB watts. Or if I convert it to dBm, I would have the power in dB watts plus 30 gives minus 98 dBm, which is a significant amount of power in a wireless communication system. So let's look at that as you would see it in a spectrum analyzer that has perfect sensitivity. So here's a perfect spectrum analyzer. One of the key parameters in a spectrum analyzer is the resolution bandwidth, and that is the width of the filter that is ahead of the power meter in the spectrum analyzer. So if I put a resolution bandwidth of 1 megahertz right here and just took this diode with 10 milliamps through it, I should see shot noise in that 50 ohm resistor that's at the minus 98 dBm level. Again, that was assuming all the current from this diode goes to the 50 ohm resistor, which turns out probably not to be true. If I change the resolution bandwidth down to 0.1 megahertz, then the noise into the power meter after the filter drops by a factor of 10. And so we'll get a 10 dB reduction in noise level. And if I went down to a 10 kilohertz resolution bandwidth, the noise in the spectrum analyzer would drop. So the lesson here is that the amount of power you see in your spectrum analyzer depends on the filter width. There is no particular frequency associated with shot noise. It is white in nature, meaning that the noise is relatively frequency independent up to some point right here. Where here I showed it 10 gigahertz being flat. But would this continue on forever? Well, there's a certain time associated with this diffusion recombination operation. And so depending on that time, if it was a picosecond kind of thing, then maybe you're going to have hundreds and hundreds of gigahertz of bandwidth. But eventually that will break down. It won't keep on going forever as we go higher and higher in frequency. Okay, so there's some shot noise view in the frequency domain with the spectrum analyzer. Let's look at it in the probability and the time domain of shot noise. So here we have a hypothetical display of noise or signal versus time if we put a diode into an oscilloscope. And so we're going to have a whole bunch of different traces, and they're going to be laid on top of each other. And we'll have if we took a cross-section, this AA cross-section right here, we'd find that there would be a distribution. The most probable voltage would be 0 volts, but there'd be some probability of a positive voltage and a probability of a negative voltage. And so if we had 5 milliamps of current in that diode, the forward bias diode, and all the shot noise went to a 50 ohm resistor, if we looked at that histogram, it would look something like this right here, where in microvolts, we'd find that the RMS value of that shot noise would be on the order of 2 microvolts. And so we would get a distribution that shows that it's highly probable to have 0 volts. It's not very probable to have a 5 microvolt level, but in this region right here where most of the voltage occurrences will happen in this histogram from the oscilloscope display. Okay, let's go look at a measurement. So I'd like to measure with this Keysight SSA-X source signal analyzer baseband input, directly measure the shot noise in a forward biased PN junction diode, just to show you that's a real measurable effect. So this circuit right here has a couple SMA connectors on it. This SMA connector is connected through a resistor to a 2N2222 BJT diode on the base emitter junction right here. And we also have an AC coupling of the noise from that forward biased PN junction diode to another SMA connector. And that SMA connector is going to connect to the baseband input of this SSA-X, which has a very sensitive baseband receiver, which I'll talk about shortly, that allows us to measure these very low levels. But let's look at the DC and AC equivalent circuit of this test circuit next. On the left-hand side, we have the DC circuit right here, where we have a diode as forward biased. This is a p-n junction of a 2n2222A transistor. And I have a power supply that goes through a 300 ohm resistor, and I'm going to supply about 6 or 7 milliamps of current through that diode. So then I can calculate the shot noise by taking 2 times electron charge times 6.7 milliamps times some measurement bandwidth B. And we're going to use 1 hertz in this case, measurement bandwidth of 1 hertz. This is a DC circuit, but if I look at this from the AC equivalent model, we're going to have a circuit looks similar, but I also wanted to point out that this resistor right here has thermal noise. And so I've looked at that 300 ohm resistor and found that it has a 15 picoamps of thermal noise, which I talked about in an earlier presentation. My diode right here is forward biased, and it has a shot noise of 46 picoamps for a 6.7 milliamp DC current going into the diode. So this shot noise right here has a decision to be made right here, where does it want to go? So that current can flow to the load right here, this 50 ohm resistor, which is going to be this SSA-X instrument, or that current source, the shot noise current, could go through its own AC resistance of the diode. When you forward bias a diode, it actually has an AC impedance. If I do a calculation based on diode theory, if I have 6.7 milliamps of current, the AC impedance of that diode would be 3.9 ohms. So this shot noise right here actually has a decision where to go. Does it want to go to the 3.9 ohm resistor or the 50 ohm resistor? Since 3.9 ohms is much smaller, most of the shot noise will flow into this right here, and not so much will flow into the 50 ohm load. So there's 46 picoamps of total current. What is the fraction that shows up here? That's what I'm interested in. So if I want to find the voltage across that one right here, I'm going to take this 46 picoamp of current. I'm going to use something in circuit theory called the current divider. So if I take that resistance over the sum of these two resistance, that will show you the fraction of current that is going out in this direction. So 46 picoamps times this current divider, which is going to be a relatively small number. And that will be the current flowing into the 50 ohm resistor multiplied by 50, and I get the resultant voltage. And so if I do 20 log of that, I get minus 195 dB volts in a 1 hertz bandwidth. And so that's what we should expect to measure in our SSA-X. I have some side notes right here. I want to talk about this AC impedance calculation that I just had done on the previous page. A classic diode has a current on the vertical axis versus a forward voltage on the horizontal axis that looks like this. It's very little current, and then when you get to some threshold, the current takes off like crazy. The turn-on voltage of the diode, which is typically around 0.6 to 0.7 volts. Now, the AC resistance has to do with how much is at your bias point, and this is my chosen bias point right here. How much is the change in voltage across the diode over the change in the current across the diode? That's the AC resistance. And it turns out that for a classic diode that has this diode equation where the current in a diode is some small current value times an exponential of the DC bias divided by 26 millivolts. If we do a derivative on that to get the AC, we find that the AC resistance is 0.026 divided by DC current. And that's the AC resistance of that diode. Now, that's not a real resistor in terms of it does not generate thermal noise. It's just a differential impedance. And so we want to make sure from last time to recognize that although we sometimes model it as a resistor, it does not produce thermal noise. Now, in the previous slide, we have two resistors right here. We have this AC resistance, which represents the dynamic resistance of the diode. We have this other resistor, which is a real resistor. That real resistor produces thermal noise. This one does not produce any thermal noise. But now we have two sources of noise in this circuit, thermal noise and shot noise. And so how do those noises add? And so the noise sources themselves are uncorrelated. They have statistically no connection between each other. So they're going to add as root sum square, which I illustrate right here. So all uncorrelated noise sources, voltage or currents, add as root sum square, and noise powers add directly. So in this case, I have 15 picoamps of thermal noise from that resistor, and I have 46 picoamps of shot noise from the forward bias diode. And if I do a root sum square calculation, the total noise, effective noise of these two current sources adding together is the square root of 15 squared plus 46 squared, which is 48 picoamps. So this resistor noise right here, the thermal noise, has almost no effect. And the only important noise in this particular one is the shot noise, which is what we're trying to measure right here. And then most of the shot noise ends up going into the AC impedance, but a small fraction of it goes into the 50 ohm resistor right here, which we're going to try to measure with this SSA-X instrument. Okay, so let's do this measurement of shot noise in a very sensitive receiver. So this is the diagram that shows the device center test, which is a shot noise input, and we have a receiver, and the receiver has some amount of gain. I've chosen a gain of 50 dB, and we're going to find out that's not a simple receiver. That has two parallel paths. Let's look at that. So the baseband input of the SSA-X has this correlation receiver. So we start out with our shot noise into a 50 ohm resistor right here. And we're going to try to measure that. So here I'm showing that that's a complex number, and I've arbitrarily assigned that at some frequency that shot noise at the input is going to have 1 unit of amplitude at a 45-degree angle. And we're going to take that shot noise and apply it to both two channels that have identical gain, channel 1 and channel 2. Now, channel 1 and channel 2 have their own noises too, but they are uncorrelated with each other, and they're uncorrelated with the input 50 ohm shot noise. I arbitrarily assign the noise of this channel 1 as 0.5 units at angle of 125, but in actual fact, it could be any angle. And I assign this one having the same amplitude of noise, but at a different angle right here. Then I take these three sources of noise, the shot noise from the diode, the two noise sources that are generated in these channels, and we go into an analog to digital converter, and we do a fast Fourier transform FFT operation on it. And what comes out of that block is we get a channel 1 signal at a particular frequency, which is going to be the input noise right here from the shot noise, plus the noise of this channel 1 amplifier. On this channel, we get the input noise from the shot noise source, plus the channel 2 noise. And then and here it shows how the input noise and the channel noise add vectorially. In this case, my input noise, my channel 1 noise adds vectorially to this 1.2 angle of 80 degrees vector. And my channel 2 output after FFTing gives you the input noise plus the channel noise gives you a vector that's 0.9 angle of 20 degrees. Now in the output, we do this magical operation called the cross correlation, which means we're going to take the voltage from channel 1 and we're going to multiply by the complex conjugate of channel 2 at a particular frequency. And we'll do this many times and average it. I do it one time here in this diagram where I take that voltage and I take this voltage conjugate, multiply them together, I get a number of 1.08 angle of 60. Now that's not quite exactly what we had to start with, but it's close. And given the fact that we had amplitudes of 0.5 in the noise, we've actually got some noise suppression going already the first correlation time. And we're going to do tens of thousand correlations. And after a time, this will converge to the value of the input noise with really good sensitivity. So it's a really good technique for measuring very low noise signals. So here we go. We're going to take this this circuit we just described earlier. We're going to take the shot noise from a diode. We're going to have some of it go here, some of it go here. But my prediction is that with this current divider, we're going to see about minus 195 dB volts based on this model right here showing up in the baseband noise measurement. Okay, let's do it. Let's do this measurement. Okay, here's the measurement result I got from that. So first, what I did is I took this very sensitive baseband noise receiver and I put a short circuit on it. And so the short circuit has no noise, and this level right here represents the noise that is found with a short circuit. In this case, on the average of 2 million. These are the number of correlations, cross correlations we did right here. So after 2 million cross correlations, that's the noise floor with no noise at the input. And then I hook up this circuit right here, which is my shot noise from the diode. And I said that we should get about minus 195 dB volts. And we measured it. We found about minus 190 dB volts right here. So don't know where this model is perfectly wrong, but I'm sure the AC was a very big guess. It's probably something different. We had a little bit more signal going from the output from the shot noise than we did in this theory right here. But still, it's pretty close, and it's just a really, really tiny signal. It's really amazing that this correlation receiver can measure the very small noise that comes from this particular circuit that I built. So in summary, shot noise. What is shot noise? Shot noise in a forward bias diode has to do with the N-type electrons diffuse across the junction to the P-type material, but that diffusion happens at discrete times and random times. And that is a source of shot noise, that random emission and random recombination time. Similarly, the holes will diffuse across the junction. When it gets to the N-type material, they'll recombine, and it takes time. That's random emission, and we get this lumpy noise right here. And so it's not a regular emission of electrons to the external circuit. It's irregular, it's lumpy, and that's the source of shot noise. So next thing we'll do after this presentation, we'll start looking at another kind of diode noise, which is reverse biased breakdown noise, which is even stronger than the forward biased shot noise, but it's still just a form of shot noise. And so I hope you had a good time learning about shot noise in forward biased diodes. Thanks.